We're going to talk about a real communication system today, so-called modulated communication systems. The idea is, of course, instead of using baseband signaling, we're now going to shift the message signal up to a higher band of frequencies. This allows it to get through wireline and wireless channels more easily. We'll talk about the transmitter and receiver. Turns out we already understand how these work. Once I show you how their function, you know how to think about them because we've already talked about it in previous videos. And finally, we'll compute the SNR that results when you use modulated communication. So, what does the transmitter look like for modulated communication? It's very straightforward. So here's our message, and we get this somewhat curious thing in which we add 1. And the assumption here is that the amplitude of the message has been scaled so it's less than or equal to 1, which makes this greater than or equal to 0. Now the reason for this has to do with there are some receivers that require that this be a positive quantity, but not all. But in order to satisfy everybody, most amplitude modulation systems do this, adding this offset and then scaling the message accordingly. The transmitter provides a gain, usually A is a big number, and multiplies by a cosine at what's called the carrier frequency. And so the idea is that the cosine here is carrying the message. That's the idea. And so FC defines the characteristics of the transmitter. So there's how much essentially power is radiated is determined by A, and what frequency range is used is determined by FC. So it's easier to understand what's going on here by looking in the frequency domain. So here's my typical message spectrum. I'm assuming it has this rooftop look. And as we know from previous videos when we talked about the Fourier transform, we've already figured out the spectrum of such signals like this. So you get a line spectrum corresponding to the fact that that periodic portion comes out by itself, added to this, and you multiply a low-pass message by a cosine, shifts it up and down in frequency, so you get these two replicas of the message itself. Now I want to point out that the message bandwidth here is W. Don't forget bandwidth is defined to be the part of the positive frequency axis devoted to the message where it has power. Well, for the modulated message, it looks like it has twice the bandwidth of the original message. And this is always true for simple amplitude modulation, is that the transmission bandwidth doubles. And that's just a fact of life. And this kind of transmitter is rather easy to deal with. This fact that it doubles the transmission bandwidth won't be that much of a factor. So let's look at more detail at some of the consequences of using this kind of scheme. Suppose we have two different modulation communication schemes going on at the same time. So one of them is using a carrier frequency 1, the other one is using carrier frequency 2. As we know from the wireless situation, if both signals come in my receiving antenna, so I get them both. Well, as long as these two spectra do not overlap, I can bandpass filter and remove the second unwanted signal. I don't have to even know it's there. This is called frequency division multiplexing. The word multiplexing means using more than once. And what we're doing is separating signals in frequency. So all radio stations are all transmitting on their own carrier frequencies at the same time. So if you look in the time domain, you'd see this mess. All cell phone signals, all radio signals, all those signals are all occurring at the same time, but in different frequency bands, which means they're being separated in frequency, which means simple bandpass filtering will allow you to focus on the message that you want. Now there is a little problem here. Suppose the second carrier was not well designed, and suppose it overlaps in frequency with somebody else. Well, now neither of these signals can be demodulated without error. This overlap here we'll cause interference, and it's something you can't get rid of by linear filtering at all. So this is bad. So it turns out you have to have some mechanism for regulating these carrier frequencies and these bandwidths so that there's no overlap among all the various uses that are used in wireless communication, and that's where government comes in. In the United States, the regulation for what each frequency band can be used for is very tightly regulated. And this is a rather beautiful depiction of what can occur in every frequency band. And so let's go through this a little bit. This is a logarithmic frequency scale, first of all. Frequency increases going down the page. It starts at 3 kilohertz, and this first one goes up to 300 kilohertz. The rest of these are 1 decade, 300 kilohertz to 3 megahertz, 3 megahertz to 30 megahertz, etc. Down here, at very low frequencies, you probably can't read that, it says not allocated. You can do anything you want up to about 10 kilohertz carrier frequency. Like I said, for wireless, it doesn't propagate very well at all, and no one's going to really care if you build your own transmitter at that frequency range. It won't go very far, so it doesn't interfere with anybody else. But above that, it's very tightly regulated. The highest frequency here is 300 gigahertz. That's very, very high. And everything in between, you can see, is modulated. The AM radio band is here. The FM band is somewhere here. And it may look like the FM band is narrower than the AM band, but that's only because this is a logarithmic scale. This is going from 300 kilohertz to 3 megahertz. This scale goes from 50 megahertz up to 30 megahertz up to 300 megahertz. So this bandwidth is actually much wider than it appears. And things become busier, if you will. More things are allocated because it's the bandwidth that matters. In a logarithmic scale, things look much more compressed than they would be on a linear scale. I would point out that in some frequency bands, you can use them for more than one thing, as long as you don't interfere with somebody else. But there's so much demand for carrier frequencies that some of them the government regulates them to be multi-use. We have to do that. And actually some are reserved for radio astronomy. It's kind of interesting. I think that's one of the bands that's reserved for radio astronomy. Interesting. Okay, well, how are we going to receive this thing? How are we going to receive a amplitude modulated message? So this is what we get, comes out of the channel and in the frequency domain. We get the broadband noise, white noise, and there's our message signals. And pretty clearly we want to get rid of all this stuff, that out of band noise, and we do that by bandpass filtering. So this stands for bandpass filter. It has a center frequency equal to the carrier frequency, and has a bandwidth of 2W because that's the frequency range. So once you go through that bandpass filter, this is what you get. You're only left with in-band noise and the message that we want. Now, I'd point out that the message that we want is not at the right frequency. The original message started down here. How do we get the message down in frequency back to where it originally started? We put it up here originally so we can get through the channel. This is the transmitter matching the channel's characteristics. Antennas work much better at high frequencies than at baseband. So we did that, we got it through, but now we have to move it back. How do we do that? Well, little surprise here. So let's look at this little mathematical property. Suppose we take x and multiply it again by a cosine. So the original transmitted message was a times 1 plus m times a cosine, and multiplying it again by cosine gives me cosine squared. What's cosine squared of theta? Well, cosine squared of theta is 1/2 times 1 plus cosine of 2 theta. So we wind up with something at twice the carrier frequency that we started with. Let's expand this. So there's the first part, and you get the same thing times this cosine. So, believe it or not, remodulating by the cosine gives us back a signal that's now in its original frequency band. We also, though, have a signal that's sitting up at twice the carrier frequency. Well, I think I know how I'm going to get rid of that. I'm simply going to filter it out to get rid of that. And when I do that, I'm left with my original message. So this is the where we started coming out of the front end. And after multiplication by the cosine and low-pass filtering, we wind up with our message down where we want it. We're going to low-pass it to get rid of these things, and we're just going to have to live with the noise that wound up in the same band. And that's where we'll have to calculate a signal-to-noise ratio. So here's the demodulator in all of its glory. Consists of what we call the front end, which just is a simple bandpass filter to get rid of extraneous communications, interference that we don't care about, and to get rid of out-of-band noise. And as we know, that gives us a spectrum that looks like this. Then after we multiply by a cosine and low-pass filter, we're left now with our demodulated message consisting of the original message, that's what we want, plus noise. So we need to calculate some signal-to-noise ratios. Well, for all kinds of reasons, I want to compute the signal-to-noise ratio here and here. So the front-end output is going to be of interest because it's a little bit simpler to compute, and also it has it's interesting to compare these two SNRs. So for the front end, the message part is easy. So this is just x of t times the amplitude that we used, and this is the attenuation introduced by the channel, and this is the power in this. And it turns out that power, that 1/2, comes from the cosine, basically, because the power in a cosine is half. And if you work it all out, you easily decide that this is the power in the message. The power in the noise is just as easy, in fact easier to calculate, because it lives in a frequency band that's centered around the carrier frequency, and so its bandwidth is 2W, and you multiply by 2 times n0/2, 2 for positive and negative frequency, n0/2 is the spectral height. And we wind up with a signal-to-noise ratio coming out of the front-end filter that's given by this expression, which should look pretty familiar compared to the baseband case. Clearly the transmitters amplitude gain is to compensate for the attenuation introduced by the channel. And the bigger the noise is, the smaller the SNR and the less happier we're going to be. And the smaller the attenuation, the less happy we're going to be. The SNR may not be good enough. Well, now let's calculate the signal-to-noise ratio in M hat. So to do that, we simply look at the message part. And on a previous slide, I showed you after you multiply by the cosine, what you get for the message part. And it's just going to be this power, which I think is pretty easily seen to be that. You square all the constants out front in the power in M. I should point out that the power in M is not very big. I essentially don't consider it because remember, we imposed the condition that the amplitude of the message signal never got bigger than 1 in absolute value. So this power is not a big number. On any gain that's provided in an amplitude modulation scheme is provided by the transmitter through A. Now the noise is the part where we have some fun. So after you do the moving up, moving down of the spectrum and wind up down here, the message part is given by the noise power spectrum in R tilde, the part of R tilde that's related to the white noise. I call that N tilde. After multiplying by the cosine, that power spectrum got shifted up and down in frequency, and they both wound up here. There are other parts of it wound up in frequency ranges we won't care about because they're going to be filtered out. And the over 4 again comes from the power considerations in the cosine. So all we have to do is add up these components here. So we get a 2 for positive and negative frequency. Each of those had spectral height n naught over 2. The bandwidth here is W. And the 2 comes from the fact that powers add. That means their power spectra add. So they're both constant power spectrum, so you just get a factor of 2. And the over 4s is because we're already in the power domain here. We're from that power spectrum, so we get the over 4. Put it all together, the noise power is n naught W over 2. So that gives us a signal-to-noise ratio that's received in the received message that's given by this. It turns out you can show that there is going to be no other receiver that gives you a bigger signal-to-noise ratio than that quantity. So this is what we call optimal. You can't do better than this. And so you cannot improve the signal-to-noise ratio over this quantity. And it depends on channel and transmitter characteristics in an obvious way. Now, I would point out that the SNR here is half of what it is here. So there's a gain in this receiver part by a factor of 2 over the SNR that's here. And it's a very interesting story about how that comes about. It's not at all obvious, and I have to leave that for another day. So now we have a characterization of virtually all modulated communication systems, at least in terms of amplitude modulation. So the transmitter multiplies the message by a cosine. The receiver has a front-end filter followed by another essentially modulation scheme followed by a low pass. These are very easy to build and construct. So because we amplitude modulate, we can choose these carrier frequencies and now send many, many, many signals all at the same time, but in different frequency bands. This is the advantage of thinking about signals in the frequency domain. In communication systems, it's very clear. Frequency domain is very, very important to understand. We also move it up in frequency, so it gets through these wireless channels more easily. Antennas work much, much more efficiently when you move them up in the way that we've seen. You now have the multiplexing situation. You can do this multiplexing, and this signal-to-noise ratio we wind up with is fundamental. Very important to remember this. This is a guideline for how well a system you may be concerned about works in terms of the amplitude provided by the transmitter and how much the attenuation is in the channel. And don't forget, we've assumed that alpha is some constant divided by the distance between the transmitter and receiver. So the further away you are from the transmitter, the smaller your SNR is going to be by the square of the distance.